Now combination of two lenses when they are not in contact, then how we going to find equivalent focal length? This is lens 1, this is principal axis. Let incident ray AB incident on this, so it will bend towards principal axis, so light will follow path like this. So this is position of image formed by first lens. This was the original path of light. Let this height from optical center of first lens, that is C1, be H1. So this is the angle of deviation produced by first lens. Now if I take one more lens here, these are the thin lenses, and this ray will move up to here, but here the second lens will further bend the ray, so ray will not follow this path. So finally it will follow path like this. This is angle of deviation produced by second lens. Let it be delta 2. This is lens 1, this is lens 2. Now this angle is also delta 2, vertically opposite angle. This is original ray and this is emergent ray, so this angle is total angle of deviation, delta. Let this point be B, this point be C, this point be D, this point is C2, this point be E. And distance between these two lenses be small d, that is BC is equal to D. So what we can write? First we can write in triangle this BED. This is a triangle BED, DBE. This angle, interior opposite angle of this. So sum of these two angles is equal to this angle, triangle property. So we can write in triangle BCD, delta is equal to delta 1 plus delta 2. Sum of opposite interior angle of a triangle equal to external angle. So this is first equation. Now we know that deviation produced by a lens, is h upon focal length. This we have already seen. Let this height be h2. So for delta 1 we can write h1 upon f1. For delta 2 we can write h2 upon f2. So I am putting this is h1 upon f. This is total deviation produced by combination. So if I put a single lens here, this point be P. If I put a single lens here, then this will be incident ray, BABE will be incident ray, and EDI will be emergent ray. So angle of deviation will be this. It means at place of delta we can write h1 upon f. Similarly at place of delta 1 we can write h1 upon f1 plus h2 upon f2. This we can write. Now see here, C2 is H1, DC2 is H2. So here CC2 is H1, DC2 is H2. So CD is CC2 minus DC2. From this geometry I can tell like this: CD is equal to H1 minus H2. In triangle BCD, in this triangle I can write tan delta 1 is equal to CD upon BC. So BC is CD upon tan delta 1, and as delta are small, so CD is upon, at place of tan delta we can write delta 1 only, and delta 1 will be H1 upon F1. Now from here if I write CD, so CD will be equal to BC into delta 1, that is BC is D, small d, so small d into, this is H1 upon F1. So at place of CD we can write this, so here we can write D H1 upon F1 is equal to H1 minus H2. So H2 will be H1 minus dH1 upon F1. So this is H2. Now I am putting value of H2 here in this expression. So H1 upon F is H1 upon F1 plus H2, that is H1 minus dH1 upon F1 whole divided by F2. So this is H1 upon F1 plus H1 upon F2 minus dH1 upon F1 F2 H1 upon F. So if I take H1 common and cancel it, so what is left? 1 upon F is equal to 1 upon F1 plus 1 upon F2 minus D upon F1 F2. So this is equivalent focal length of this combination of lenses when lenses are not actually in contact. So this is the formula. At place of this we can write power of equivalent lens. This is power of first lens plus power of second lens minus D power of first lens into power of second lens. So these are the two expressions should remember. But this expression is applicable or true only if incident ray is parallel to principal axis. So remember this restrictions. This relation, this is valid only if incident ray AB is parallel to principal axis. Only then this relation you can use. If object is at finite distance, if object is somewhere here, then you can't use this relation. Then you have to take a refraction from first lens first, then image of first lens will behave like object for second lens, and then take a refraction through second lens and find final position of image. So you have to take a refraction through lenses separately. You can't use this formula. So this formula is valid only if incident ray, this ray is parallel to principal axis. So remember this result. So this result only is important for NEET. For IIT, this is one step ahead. You should know, means if I replace these two lenses, where I have to put equivalent of these two lenses, you have to put equivalent of these two lenses somewhere here. So this is the position of equivalent lens, means this much distance left of second lens, or PC2. So PC2 distance before the second lens. Equivalent lens should be kept PC2 distance before the second lens. And suppose if you calculate PC2 distance and it comes negative, it means that equivalent lens should be kept right of second lens by the same distance. So remember this. So you can calculate PC2. PC2 you can calculate by using this right angle triangle. This right angle triangle, PC2 you can calculate. So position of equivalent lens with respect to second lens, if you want to find, you can find position of equivalent lens with respect to second lens. So here we have to calculate PC2. This we have to find. So see, in triangle ECD, in this triangle, if I take tan delta, then it is perpendicular CD upon base EC, and you know EC is equal to PC2. So here we can write PC2 also. So CD is equal to PC2 into tan delta. At place of tan delta we can write only delta. Now CD is H1 minus H2 is equal to PC2 into delta, and delta is H1 upon F. Now H1 minus H2 you have to find. H1 minus H2 is dH1 upon F1. So here we can write dH1 upon F1 is equal to PC2 into H1 upon F. H1 cancel. So PC2 is D into F upon F1. So this is your answer. So where equivalent lens should be kept, it should be kept this much distance before the second lens. So second equivalent lens should be kept D F upon F1 distance before the second lens. So this is your answer. So remember this. Now let us see one question on this. Now it is given that two convex lenses of focal length f1, f2 are kept d distance apart coaxially. Separation between them is d. If a parallel light is incident on first lens, an emergent ray from second lens is also parallel to principal axis, that is given. Then find value of D in terms of F1, F2. This is the question. Find value of D in terms of F1, F2. Here incident ray on first lens is parallel to principal axis and emergent ray from second lens is also parallel to principal axis. You have to find a relation between F1, F2 and D. To see solution, first let us solve it diagrammatically. So diagrammatical solution, suppose this is principal axis. If parallel ray is incident, then we know that after refraction it will pass through focus. So it will go through focus like this. So this is the F1 from lens 1. Now this is second lens. This ray is incident on second lens and after refraction it becomes parallel to principal axis. Only then this situation will be achieved. So when object is at focus, then after refraction rays become parallel to principal axis. So here object distance is equal to focal length of second lens. And it is given this separation between two lenses is D. So D should be equal to F1 plus F2. So D is equal to F1 plus F2. So this is diagrammatical solution of this question. Now see analytical solution. Suppose this lens is not bending light, it means its focal length should be infinite. This lens is not bending light, it means its focal length should be infinite. Equivalent focal length. So equivalent focal length is 1 upon F1, 1 upon F2 minus D upon F1, F2. If it is infinite, then this becomes 0. So it is 0, 1 upon F1 plus 1 upon F2 minus D upon F1, F2. I move this on this side. So D upon F1, F2 should be equal to this if I take LCM. So it is F1 plus F2 upon F1, F2. Now F1, F2, F1, F2 cancel. So D is equal to F1 plus F2. Same result you got by solving this equation. So this is analytical solution, this is diagrammatic solution of this question.